I want you to picture something for a second. You're standing in your backyard, and you're holding this lump of black, lightweight material.
Mm.
It's dark, it's crumbly, and it leaves that annoying, greasy smudge on your thumb. If I handed this to you without any context, your first instinct is probably, okay, where are the marshmallows?
Let's fire up the grill because it looks exactly like charcoal.
It looks identical to the stuff I buy at the gas station. But if you tried to cook a steak over this specific stuff, you'd be missing the point entirely.
Well, completely.
In fact, you'd be burning up something that the scientific community is, they're treating it like black gold.
And that is not an exaggeration. We aren't talking about fueling a fire today. We're talking about a material that acts less like fuel and more like a high-tech sponge.
Exactly. And honestly, before I dove into this stack of research, and we have a lot here, papers from agricultural institutes, reports from the FAO, climate data from the IPCC, I thought biochar was just a fancy marketing word.
Right.
A rebrand to sell charcoal at a higher price.
Right. That is the most common misconception. Isn't this just burnt wood? And the answer is a hard no. The difference isn't just semantics, it's geometry. It's chemistry.
So that is our mission for this deep dive. We're going to unpack why this specific black powder is being positioned as a triple threat solution.
A triple threat. I like that.
We're talking about lowering farming costs, fixing damaged soil, and this is the big one, fighting climate change on a planetary scale.
It's a tall order for something made out of, old corn cobs.
It really is. So let's start with the basics. I drive to the store, I buy a bag of briquettes, that's charcoal. How is biochar physically different from that?
Yeah.
Why can't I just crush up my Kingsford briquettes and throw them in my garden?
Please don't do that. It really starts with the intent and the ingredients. The charcoal you buy for a grill is designed to burn. It's fuel.
Right.
Its whole job is to release energy as heat. And it often has additives to help it light or binders to keep it in that briquette shape. Biochar is, we call it biological charcoal. It's made from biomass organic waste.
We're talking rice straw, corn cobs, tree branches.
Even animal manure. But the magic isn't just what it's made of, it's how it's cooked.
Okay.
If you burn a pile of leaves in your backyard, what happens?
It just burns. You get ash, smoke, and heat. And eventually, just a pile of gray dust.
Right. The carbon in those leaves reacts with oxygen, turns into CO2, and just flies off into the atmosphere. You're left with white ash, which is just minerals, calcium, potassium, but the carbon structure is gone.
Obliterated.
Biochar is made through a process called pyrolysis.
Pyrolysis.
Yeah.
This is a key term in the reading. This is burning without oxygen, right?
Or in a very low oxygen environment. You heat that biomass, usually between 300 and 700 degrees Celsius, in a sealed or limited air container.
Okay.
And because there's not enough oxygen to feed a flame, the material doesn't combust to ash. Instead, it thermally decomposes. The volatile gases burn off, but the carbon structure, it kind of freezes in place.
This is the part that blew my mind. The research described it as a skeleton.
That's a great way to visualize it. Because the material doesn't collapse, it retains the cellular shape of the original plant matter. If you look at biochar under a microscope, it doesn't look like a rock.
No.
It looks like a sponge or honeycomb. It is incredibly porous.
I want to double click on that because the stats in the source material were insane. Imagine the surface area of this stuff.
It's mind-boggling. Just 1 gram of high-quality biochar, we're just talking a piece the size of a pencil eraser, can have a total internal surface area of anywhere from 200 to 400 square meters.
Wait. So one little lump has the surface area of a tennis court.
Essentially, yes. It is just full of microscopic tunnels and holes, and that geometry is the secret. That's why it works. It's all about surface area.
And unlike the compost I throw in my garden, which disappears in 6 months, this structure is stable.
Correct. Compost is what we call labile carbon. It breaks down fast because microbes eat it up. Biochar is recalcitrant, or stable carbon. Because of that heat treatment, the carbon bonds fuse into these aromatic rings.
So they're tougher.
Incredibly tough. It can sit in the soil, maintaining that sponge structure for hundreds or even thousands of years.
So instead of a solid block of fuel, we're burying a permanent carbon skeleton into the ground.
Exactly. You are building infrastructure in the dirt.
Okay, so we've got this empty skyscraper structure. Let's pivot to why a farmer would care. Why does the soil need empty skyscrapers?
Right.
Because if I'm a farmer, I care about yield and I care about cost. I don't necessarily care about burying carbon skeletons unless it does something for my crop.
And it does. Because healthy soil isn't just dirt. I mean, we tend to think of soil as this dead, static thing holding plants up. But healthy soil is a living ecosystem. It's a jungle.
And the biochar provides the housing.
Precisely. Those microscopic pores, the apartments, provide a safe habitat for beneficial soil microbes, bacteria, and fungi. It gives them a place to live, to breed, and to hide from predators.
So we are building fortified housing for the workforce that keeps the soil healthy.
And that workforce is struggling right now. If we look at the reports on modern farming, what are we seeing?
Degradation. I mean, the FAO reports are pretty grim. Compaction, loss of nutrients, salinity. It feels like farmers are pumping in more and more fertilizer just to get the same yield they got 10 years ago.
That is the vicious cycle. Chemical fertilizers are salts. Over time, coupled with heavy machinery, they kill off the biology and compact the soil. The ground becomes like concrete. Roots can't penetrate it, and water just sits on top or runs off.
The sources used a Thai phrase, "rongkai," "wonsui," to describe what biochar does to that concrete-like soil.
Loose and aerated. It's a physical change. Because biochar is rigid and porous, when you mix it in, it prevents the soil from compacting. It keeps air channels open so roots can breathe.
And I assume that honeycomb structure helps with water too.
Drastically. Think about a sandy soil. Water runs right through it like a sieve. If you add biochar, those cores grab the water and hold it. It acts like a reservoir, releasing moisture slowly as the plants need it.
In a world where drought patterns are getting so erratic, that's not just a nice to have, that's crop insurance.
It is. But here is the piece that I think really changes the economics for the farmer. We talked about water, but that sponge also holds nutrients.
This is the nutrient bank concept.
Right. And to understand this, we have to get slightly technical for a second. We need to talk about CEC-cation exchange capacity.
I saw that acronym all over the research papers. Break that down for us.
Okay. So ideally, you want soil to be like a magnet. When you throw fertilizer, nitrogen, phosphorus, potassium onto the field, those are charged ions. You want the soil to grab them and hold them.
So the plant can access them later.
Exactly.
But in degraded soil.
The soil has a low magnetic charge, or low CEC. So you spray your expensive fertilizer, it rains, and the fertilizer just washes right past the roots and into the groundwater.
It's literally money washing down the drain.
And polluting the water table while it's at it.
Right.
Biochar has a very high CEC. It's highly charged. It absorbs, that's absorbed with those nutrients. It grabs the nitrogen and phosphorus and holds them on its vast surface area.
So it creates a buffer. It catches the nutrients so they don't wash away, and then hands them over to the plant roots when they need them.
Which means the efficiency goes way up. The research suggests a farmer can potentially use less fertilizer, but get the same or better results because the plants are actually getting what was paid for.
That's the ROI. That's where this stops being an environmental theory and starts being a business decision. Less fertilizer equals lower production costs.
It's a shift toward precision management. Instead of just dumping chemicals and hoping for the best, you are conditioning the soil to be a better engine for growth.
So if you're a farmer, biochar is a soil conditioner, water tank, and a savings account all in one. That explains the agricultural obsession.
Yeah.
But the sources we're looking at today don't just stop at the edge of the farm. They zoom out way further.
If we connect this to the bigger picture, we have to talk about the climate.
This is where the UN comes in. The sources explicitly mention the IPCC. Why is the Intergovernmental Panel on Climate Change looking at burnt corn cobs?
Because biochar is unique. It is one of the few technologies we have that is truly carbon negative.
We hear carbon neutral a lot, but negative implies we are actually subtracting.
Think about the life cycle of a plant. A corn stalk grows. How does it grow? It sucks CO2 out of the air. It builds its body out of carbon.
Right, photosynthesis.
Now, usually that corn stalk dies. It rots in the field. As it rots, that carbon reacts with oxygen and goes right back into the atmosphere as CO2. Or worse, it releases methane. It's a zero-sum game.
Carbon came from the air, and it goes back to the air.
Or if you burn it, it goes back instantly.
Instantly, yeah.
Exactly. But with biochar, you intervene. You take that plant matter, you pyrolyze it, and you lock about 50% of that carbon into that stable black structure we talked about.
And then you bury it.
You bury it. And because it doesn't rot, that carbon stays underground for centuries. You have physically removed carbon from the atmosphere and put it back in the Earth's crust.
That's a lot simpler than I expected.
Mm-hmm.
We always hear about these massive high-tech carbon capture plants that look like giant fans sucking air.
Right.
This is just cooking plants and burying them.
It is low-tech carbon removal. And it's scalable. The IPCC identifies this as a legitimate carbon removal technology, or CDR.
And there was another layer to the climate impact, right? Something about the soil itself
Yeah.
burping.
Yes, soil burps. Agricultural soil emits greenhouse gases, specifically nitrous oxide.
Which is way more potent than CO2.
About 300 times more potent. It comes from nitrogen fertilizer breaking down. Research shows that adding biochar to soil changes the microbial environment in a way that can significantly suppress those nitrous oxide emissions.
So it stops the soil from emitting bad gas. And indeed, it locks carbon underground. It's a double whammy.
And that is why the FAO views this as a critical tool. They see it as a way to restore degraded land to ensure we can feed the growing population while simultaneously fighting climate change.
It's rare to find a solution that does both.
Very rare. Usually you have to choose between production and conservation.
It seems like the world is waking up to this. The sources mention that China, Japan, and several European nations are already integrating this into their eco-agriculture systems.
They're moving from niche experiments to national strategy.
Now, I'll bring this down to a specific context mentioned in our source material. Thailand. Because if we are talking about biomass and burning, Thailand is ground zero for a very specific problem.
You're talking about the smoke, the burning season.
PM 2.5.
Yeah.
Every year, early in the year, the air quality in northern Thailand and Bangkok just drops off a cliff. And a huge chunk of that is linked to agricultural burning.
It is a massive issue. After harvest, farmers are left with tons of biomass, rice straw, corn cobs, stalk. It's waste. It's in the way. And the easiest, cheapest way to clear the land for the next crop has historically been to just set a match to it.
It's quick, it clears the snakes, it clears the pests. I get why they do it.
Exactly. But that open burning releases massive amounts of particulate matter. It's a health crisis.
So how does biochar change that equation? Because you still have to process the waste.
It offers an alternative path. Instead of open burning, which is uncontrolled, dirty, and smoldering, farmers can convert that residue into biochar using controlled pyrolysis.
But, and I have to play devil's advocate here, open burning is free. All you need is a match. Making biochar requires equipment